Hello, everybody. My name is Hesam, and I'm a data scientist at Myfitnesspal. I'm going to talk about a problem that we have been facing in the past few years, and the solution that we ended up with using Spark, which is constructing a reliable food database with respect to the string of brand and description, and also, more importantly, the nutritional information. As a quick introduction, Myfitnesspal is the most well-known fitness and health app in the world. And it's basically tries to log and track the food and exercises for the users. And it provides like the number of calories, the number of fat, and all the nutrients being consumed each day, plus diagrams to show the progress and the capability to log the weights and show the progress of each person's performance in the last few weeks. We recently could reach more than 80 million users worldwide, which was a significant achievement for the company. And in the past few years that this app has been active, around 5 million foods have been added to our food database. And some other cool stats about the app is that, for example, in total, our users have lost around 180 million pounds, which is kind of equivalent to the weight of 120,000 elephants, and some other cool statistics about that. But the most important asset of the app has been the food database and the users' capabilities to create their own food. So this crowdsourced food data that we're dealing with is actually one of the main advantages of our app, because users can enter their own food with their own brand description and especially the nutrition facts with the very simple operations, which is this is a picture of the mobile app that is out for the smartphones. But this crowdsourced data, besides the important advantages that it provides, like helping us to grow the size of the database and also to filling in the food items that are missing, especially for the international food items, it has a very important disadvantage, which makes the database extremely noisy, and it generates a lot of inconsistencies in the food database. Although it enables users to create their own food and to customize the food items that are there in the database. And here's a couple of important issues on top of them that is mentioned here. For example, the inconsistency might happen in the string level of the brand and description. For example, the same food items like McDonald's chicken might appear in several manners, like McDonald's McChicken, or McDonald's McChicken sandwich. All these things are created by the users, but they're actually referring to the same entity in our database. Another issue, which is kind of more important, especially for the users who are trying to track the nutritional information, is that the same food item might have lots of different variations with respect to the nutritional information. For example, this is 2 different reports for tangerine, which is there in the internet from 2 different websites, which are mentioning like completely different nutritional facts for the same item. And these 2 are actually considered ground truths, both of them. But the issue would be much more significant to consider when we note that a lot of users might create the food item with incorrect nutrition information or inappropriate nutrition. So in that case, we can see that in the search result, which is the most important part of the food log process, you can see that whenever tangerine is searched for this particular query, you can see there are lots of different variations with different calories information on top of it. And this brings a lot of doubt amongst users to which item to go with and which food is the appropriate food with respect to the nutritional information to select. So in this problem, we try to solve this issue by constructing the most accurate subset of our food database. And in order to do so, we used a couple of important signals coming from users. These signals are either implicit, which means, for example, the number of times a particular food has been logged by the users, or the number of similar items with the same brand and description, with the same nutritional information that have been added to our huge database. And there are other explicit signals like the number of confirmations for the nutritional information, and also if the food is public or private, and things like that. And in order to do that, we use Spark as an important means to achieve this goal. So the reason for picking Spark was that on top of it, we had lots of different types of data, and each data was coming in a very huge size. And it generated a lot of operations to be performed offline, like a lot of table joins. And we wanted to make the whole process in a kind of unified form in a same framework that Spark provided. And also, there were a couple of very, very useful libraries of Spark, like MLlib and GraphX, that would be very helpful for the application that we're looking for. And also, the nature of the work that we're going after was kind of parallelizable, and that would be an important factor for us to speed up the process. So the data that we were dealing with was residing in Amazon S3 structure, and we had different kinds of tables, like the table containing the nutrition information, the food items with the brand and description, and for example, the signals, the number of times a particular food has been logged, and many other types of signals. So using a Spark data flow, we could register all these tables from S3 into Spark tables. And afterwards, we could operate a join on top of this data to create a single entity, somehow to merge all these different types of information for particular foods into one entity, which was a class food in our database. And in a Spark, we were dealing with the string of brand and description, the nutritional information, and also the various types of the signals that we had collected for each food item. So from now on, what we're going to deal with was an RDD of all the food items that were there in our database. Of course, a couple of high-level filtering were applied on top of the food items, but that's the size of the RDD that we're dealing with after this process was really huge. To start the process, we tried to unify the food entities that were referring to the same type. For example, different types of brand and description that I mentioned earlier for the McDonald's McChicken sandwich. We tried to make them as similar as possible with some string normalization process. For example, we did some kind of normalization containing removing the special characters like apostrophes, question marks, and things like that. But we had to be careful to keep with and without words from in the brand and description string, because that was really informative for our application. But besides that, we removed the stop words from the branded description. We sorted all the words in the string of branded description to make the process kind of order independent, and also duplicate element, which appeared a lot because users tend to add the brand in both brand and description of each food item. So afterwards, what we end up with is a normalized string for the brand and description, and this process is independent for each particular food item. So it can be run in a parallel manner and speed up the process really significantly using Spark. For the next step, to construct a subset of the food items with the most accurate information, we had to run some type of clustering on the food items that we had in the database. To do so, given the normalized strings that we created in the previous step, we tried to add that normalized string and treat it as a key of our pairs in a new RDD. So we used the map operation in Spark to get this normalized string and treat it as the key value. And also, the food itself would be considered as the value of each pair. So on top of it, all we needed to do for doing this clustering was to do group by key operation. And what we'll end up with is for each brand and description, which was previously normalized, we have a list of the food items that were referring to the same entity. Of course, there were lots of cases that, for example, the same food item might appear in completely different brand and description such that it cannot be captured in the normalization process. And to take care of it, we had to run a dedup process on top of it. So this is an example of the clustering output that we got. For example, for the coffee, mocha, Starbucks, we can see that we have a bunch of foods here. We have a bunch of foods for McDonald's nuggets and things like that. But the process would be, I mean, in this process, there might appear some food items which are actually duplicates or typos or misspelling of one of these clusters. For example, if coffee, mocha, Starbucks is misspelled, we can see that using that normalization process, this cannot be treated as the same entity, and it would be separated in two different clusters. So the appropriate thing to do here is to treat these two entities as the same entity and to merge these two clusters together. A naive approach for this dedup process was to run a pairwise comparison between all the clusters that were computed in the previous step. But as you can guess, that process was extremely slow because the size of the data that we were dealing with was around 100 million items. And for all of them, running a pairwise string comparison was not feasible. Although it's good to know that the Cartesian function implemented in Spark can generate all possible pairs from a given RDD or two different RDDs. And that was quite useful. But the nature of this process was extremely time-consuming. So in order to do that, we realized that there is a locality-sensitive hashing technique implemented in Spark. And the link to access the code is available. And what it does is to pick the candidates of the clusters that are, that are having the highest chance of being duplicates. So after running that, we can realize that, for example, the segmented picture shows the clusters that are actually candidates of being duplicated. There might be some false positives in this process. There might be some different food entities which are mapped into a single hashing bin. But as you can guess, the pairwise comparison in each bin can be performed in an independent manner and in a parallel manner. And this speeds up the process really significantly. So what we ended up with was a significant amount of time saving from a week to only a couple of hours using this hashing technique. So after clustering and dedup process, the question is which class member we need to pick and set it as a verified food item with respect to the nutritional information. Here we use the signals, the user-based signals that we talked about it a few minutes ago, which was, for example, the number of times this food has been logged, the number of times this has been confirmed, or some other important criteria, which are all kept together in the food entity that we have created in a Spark. So for each member of this cluster, we created and we computed a score, so-called quality score. And this process, again, can be run in a parallel manner and in a very fast manner using Spark. So after that, we pick the cluster member that is having the highest quality score, which is colored in green here. So that's the candidate of this cluster to be set to a verified item. But this is not the end of the story. Even the maximum element of each cluster might have incomplete or inaccurate nutritional information. So what we tried to do was to run some kind of a voting scheme on top of each cluster. In order to do that, for each nutritional information, for each nutrient like calories, protein, sugar, etc., we had a voting scheme with an emphasis to the cluster center being selected. And we actually collected the majority voting for each nutrient value and picked it as the new nutritional information for that particular food item. And of course, we set some different thresholds as the minimum number of votes, because if, for example, the calorie information cannot get enough number of votes, it's not safe to pick it as a verified item. And that after this process, we will end up with an aggregated nutrition for this cluster member. But after talking to a couple of nutritionists and getting feedbacks from a limited number of users, we realized that there are still some inaccuracies among the verified food items. And in order to tackle that, we ran some post-processing steps to run some sanity checks on top of it in order to detect the ones that are still not correct and to be the most conservative in detecting these food items. So that's pretty much the whole process. After this, we can see that previously for the query like tangerine, we had lots of different calories information. But after computation of these verified foods, we can see that in the picture in the right side, the food items that are marked by this green verified mark are the ones that are actually verified, and the calorie information for these items are very similar to each other. So now users can go ahead and pick the one that is marked as verified, because this is the one that had the majority voting. And this would, we expect that this would decrease the search process for users and also make the search experience more and more comfortable. And that's going to happen in the next few months. There are a lot of possibilities to improve the process. For example, when the verified food items are going to release to the search scenario, we can collect feedbacks from users implicitly and to see if there are some incorrect or inaccurate nutritional information from inside the verified foods. And also, more importantly, we are trying to run some kind of link analysis on top of the graph, the huge graph that we are dealing with, which is containing all the users and all the foods. And in order to do that, the Spark graphics library is, of course, of great importance. And here's the plan for our future endeavors. And that's pretty much all I wanted to talk about. I'm ready to answer your questions if you have any. Thank you so much for listening.
All right. Questions? Man, the room's, yeah.
I was just curious, for food items that might not have an explicit brand, like pad thai. There's a million different restaurants. Like, do you guys pick a single version of that dish, or do you give multiple options?
There are lots of food items that are having like blank brand, or the brand information that is, I mean, nonsense. For example, generic or homemade, this kind of stuff. But we treat them the same as the other food items. We believe that if a food item is from a popular brand, it gets more and more number of votes, number of items in that cluster. So this process automatically takes care of these cases, and these are the ones that are going to be promoted as a verified item. And if the brand is nonsense or is missing for a particular food, the chance of getting enough number of voters is really low. So it won't be promoted to a gold item. Yep.
We got time for maybe 1 or 2 more questions. Yeah.
Just 2 quick questions. Is there an authoritative, like a source from like the USDA or something around the nutritional facts? Do you guys integrate that?
Yeah, exactly. One important part of the foods and the signals that we're dealing with was whether or not the food was imported. So there are lots of different sources that we get the food items from. And yeah, that's an important signal that is almost definite for an important food from USDA to be promoted as a verified item. Yep.
And one last question. Do you sanitize the data kind of up front and drop things? I don't know, like checks like the number of saturated fat, grams couldn't possibly, account up for that many calories, this sort of thing.
Exactly. This process is there, this kind of sanity check is there when users try to input a particular food item, because if it's, for example, having negative values or the total number of protein and fat is totally off by the number of calories, the users are not able to create such foods. And this process is applied on top of the verified food items as well to be, as safe as possible in generating these items.
Maybe time for 1 more. Can't see in the lights. All right, Hesam, I get to put you on the spot now, so I get to ask you a question. So
Sure.
You went through all of these things now, basically the food clustering, and you mentioned GraphX is next. In your experience working with Spark, like what would be your wish list? What was one thing that you were like was much harder than it should have been, and you would like to see kind of come easier for kind of future work that you're doing?
That's a good question. Before answering your question, I wanted to mention that it's been only a couple of months that I started using Spark, and I found it really fluent because after a couple of weeks, I was in the position to get the data, this huge amount of data, and develop the code. And that was the main advantage that I found working with Spark. There are still a couple of runtime issues that I get, and I've been in touch with people in Databricks to make them sorted. And on top of it is the definition of the case classes. And if you define a case class in one code block and you try to call it in a function from a different code block, this produces a runtime error. And if this could have been resolved, that the code that we were dealing with could be much more organized. We could separate out the code into completely independent code blocks. But currently, we have to make this whole process into the same block, which is, kind of non-organized. But yeah, everything else that I've been dealing with was pretty cool.
Okay.
And
Great.
thank you, guys.
All right, let's thank Hesam again.
Thank you.